Good day everyone. So welcome to the third week of fundamentals of mixed signals and sensors. So for this week, our topic will be switched capacitor and switched capacitor gain circuits. Okay. So for the learning outcomes, by the end of this module, a student must be able to, number one, understand the concept of amplifiers, and number two, know the difference of various amplifiers. For the topics, we have number one, amplifiers, number two, switch capacitors, and then number three, capacitor filters. Alright. Introduction. So why amplifiers are important in sensor systems. Okay? So for a little bit of insight, so why do we have to study this amplifiers topic? Last week or last meeting, our module was all about sensors. Okay? Sensors. What about sensors and amplifiers? Okay. So when a sensor is activated by a stimuli, right? So whatever sensor it may be, a sensor usually gives an output of maybe an AC output or maybe a DC output, but usually the size of this is on the depending on the type of sensor. But if the sensor is a type that has an voltage output, usually it's in the microvolts range. Okay, so microvolts is not that visible on processor circuits. Okay, processing circuits. What will happen here is we need to convert these microvolts into bigger voltage. So that's where amplifiers come in. To amplify this signal. Okay, so from microvolts, usually amplifiers is used to at an average a signal to a 1,000 times level. So from microvolts it becomes millivolts. Okay, so then from the amplifier, it will go through other stages as well, like filters, whatsoever. Then it will go to the processing circuits. Okay, so this is the importance of amplifiers to enlarge the signal so it can be used by the processing circuits. Okay, so that's for the importance of amplifiers in sensor systems. Okay, so we'll proceed. So for our very first amplifier, we have figure 1 here, voltage amplifier with capacitive beta feedback network. Okay, capacitor ratios can be very accurately controlled in an integrated circuit with the right sizing and layout strategies, and thus they offer potential for making precision amplifiers. So the good matching properties also is attractive for building filters. The most natural structure for a capacitor-based amplifier is shown in figure 1, where if the op-amp is ideal, the gain of the circuit is, okay, so A is gain, so the voltage gain is equals to the output voltage over the input voltage, which is equal to negative C1, the value of the capacitor on the input side, over the feedback capacitor, the capacitor on the output side. Okay, so just a little recall of the, what you call this, amplifier or operational amplifiers or op amps that you've encountered so far. So I'm sure you've encountered inverting amplifiers, non-inverting amplifiers. Okay, those are the popular ones. Common mode amplifiers, differentiators, integrators. Okay, so those are usually involving resistors to calculate the gain around the amplifiers. But for this, since we are dealing with sensors and we are trying to make the amplifier as precise as possible, so in this topic we will be using capacitors since they have a good potential, okay, for making precision amplifiers. Okay, before we proceed, okay, I would like you to understand where did this equation came from, okay, how did we derive to this equation. Okay, so we have here our amplifier. So we have V in, okay, and then we have the capacitor. We can use, although in the module polarized capacitor was used, but of course we can use a non-polarized capacitor. Doesn't matter anyway. I mean, it does, but usually nowadays non-polarized capacitors are most often used, especially in very small circuits. And then we have here the feedback capacitors, feedback capacitor, then V out. Okay. Feedback capacitor. Okay. So the voltage gain is equal to V out over V in, which is equal to negative C1 over CF. Okay. Should we go straight to this? Let's go straight to this. Before we start deriving our equation, let us recall some of the properties of an ideal op-amp. Okay. So on an ideal op-amp, the current on the inverting side or inverting input is always 0. Same as in the non-inverting side. So this one, the current here is always 0. Okay, and also by the way, why is it 0? Because the ideal op-amp has an infinite or very high input impedance. Okay, and then the input voltage is equal to not input voltage. The voltage on the inverting side is always equal to the voltage on the inverting side. Okay, so this one. So those are the some of the major special characteristics of an ideal op-amp. Okay, so since this side has no current, we can assume that the current will pass through this one, going to the output. Okay, so before we let current pass through, okay, so we will use, in this case, a little bit of nodal analysis, okay, to look at the behavior of the currents. Okay, so for the nodal analysis, we know that the sum of all the currents going to a node is always equal to 0. So in this case, I1 plus I2 will be equal to 0. Okay? And then, the problem though is, this is a capacitor. This is not a resistor. So is there a current? Yes, there will be a current if this input voltage is AC. But if it is a DC, then the current will not pass through. It will be 0. Okay. But then again, if the sensor is measuring an analog signal, then the output must be AC. Okay, so it can pass through this capacitor. So we can say that there is a current. Okay, but again, what is the formula for current for capacitors? If you can still remember. Okay, so for a little bit of spoiler, that will be C1, okay, times the rate of change of the voltage. Okay. Sorry. V in plus the feedback capacitor times the rate of change of V out. You must be wondering, why is there derivative involved? Just a little recall. We've already encountered that in a capacitor, the voltage is not like I say, for example, if the maximum voltage is 5 volts at time 0, the voltage on a capacitor is not 5 volts yet, so it is increasing at a certain rate, okay, until it reaches 5 volts. Okay, so there is a rate of change for the voltage in a capacitor. At the same time, while the voltage is changing, the current is also changing. Okay, so that's why there is a derivative involved. So anyway, hope you give a review on that. Maybe read back on some of the characteristics of the capacitor or something like that. Okay, so let's simplify our equation here. So we have let's transpose this one. So CF dV out over dt is equals to negative C1 dV in over dt. Okay, now we can transpose dt. Transposing dt on both sides, it will cancel. Okay, so we will be left with CF dV space crisis. Let's drag this one above. So CF dV out, okay, is equals to negative C1 dV in. So to eliminate the derivative, we integrate both sides. So this will be CF, okay. By the way, the integration will be from t to 0. Usually it's from t to 0, okay. But if it's getting too complicated for you, I'll just remove this one. Just assume derivative for now, integral for now, just to cancel the derivative. Okay, so plus V out sorry, it's not plus, CF times V out, okay, is equals to negative C1 V in. Okay, so since this is a integral process, there should be a constant, right, a plus C at the end. But since this is an ideal process, or rather this is an ideal op-amp, we can ignore the C constant for now. Okay, then a little bit of transpose. So we have here V out over V in is equal to negative C1 over CF. So this is how the equation was derived. Okay, this is a little bit different from the from the resistor counterpart, because on the resistor counterpart this is negative RF over R1. So anyway, let's have this for now. Can you still see it if you screenshot? I'll give you 10 seconds to screenshot this one. Okay. 4, 3, 2, 1. I think we're good. Let's go back to the presentation. Okay, so this is that's how we derive the equation, ideally at least. Okay, next, it is argued that since the capacitor ratio can be very accurately controlled, the gain of this amplifier can be very accurately controlled as well. Unfortunately, this circuit does not perform as desired. Invariably, there will be a small bias current drawn from the input terminals of the op-amp. Okay, this bias current will cause charge to accumulate on the node connecting C1 and CF, and this accumulation of charge will eventually, maybe after a few milliseconds, cause the output of the op-amp to saturate, even if the capacitors were initially uncharged when power was applied to the circuits. Okay, so what it's trying to say is that since, I'll go back to the previous slide for now, this is an ideal op-amp. Okay, so this will work on an ideal op-amp. But since ideal op-amps does not exist, okay, so there are problems on this configuration. Okay, like it said, since the input of the op-amps, which ideally should be zero current, but of course on actual op-amps there will be some current or some charges that will be accumulated in here. Because of those charges, okay, it saturates the node here, okay, affecting the performance of the gain of C1 and CF. Okay, so that is the problem that is encountered with this configuration. Next slide. But a variant of this amplifier is shown in figure 2. Okay, so this is figure 2. I'll go to the next slide. So this is a bit different and with switches involved. Okay, I'll go back to the previous slide. Okay, this is termed a charge redistribution amplifier or a switch capacitor amplifier. Okay, so aside from the capacitor used to deliver the gain, okay, so they included switches. The switches are controlled by phi sub 1 and phi sub 2, which are non-overlapping clock signals. If a sinusoidal input is applied, the frequency of the two clock signals is usually much larger than the frequency of the input. The relationship between the period of the clock signals t and the input frequency is shown in figure 3. Okay, so let's go to figure 3 for now. Okay, so if this is the analog clock, okay, so this will be t sub 1, this will be t this period here, and then this will be t sub 1 plus t. We can say that in the switched capacitor circuit, this will be phi sub 1 and then this will be phi sub 2. Anyway, let's go back. The non-overlap of the clock signals themselves is shown in figure 4. Okay, this is the figure 4. Okay. I was wrong. I misunderstood it wrongly. So the t is the period of switching for phi sub 1 and phi sub 2. So t sub 1 is when the switching will start. Okay, then t sub 1 plus t will be when the switching ends. Okay, so I guess in the whole sinusoidal signal, there will be a lot of t periods wherein there will be switching time. Okay, so in this case, we have phi sub 1 and then phi sub 2, and in between phi sub 1, this is phi, symbol of phi, Greek letter, phi. Okay, small letter phi. So between the end of phi sub 1 and start of phi sub 2, there will be a non-overlapping time. Okay, so they will trigger separately. They will not overlap. Phi sub 2 will start after some time that phi sub 1 ended. So this is called the non-overlapping time, or t sub none. Okay, so this is t when compared to the whole signal. Okay, let's go back here. In this amplifier, the feedback capacitor is discharged during phi sub 1, and charge proportional to V in is stored in C sub 1. At the end of phase phi sub 1, this charge is sampled onto C1. At the start of phase phi sub 2, this charge is transferred to feedback capacitor and the output voltage becomes, okay, so this is what it's saying. At phi sub 1, these switches will turn on. Okay, when this switch turns on, V in, C1 will be charged with the voltage equivalent to the input voltage. So if this is 5 microvolts, when phi sub 1 turns on, C1 will be charged with 5 microvolts. Okay, the purpose of this switch is when this closes, okay, phi sub 1, they will close at the same time. When this switch closes, feedback capacitor will be shorted. Since the feedback capacitor will be shorted, okay, all the charges will be discharged from the feedback capacitor. Okay, so whatever input coming from C sub 1 will be taken by the feedback capacitor accurately. Okay. If it will not be discharged by phi sub 1, okay, there will be error in the output. So that's the purpose. So phi sub 1, F feedback capacitor discharged, C sub 1 charged. Okay, then this will open, phi sub 2 will close. When phi sub 2 closes, the charges from C sub 1 will discharge and it will go to the feedback capacitor, then go to the output voltage, then applying the corresponding amplification. Okay, so that's how our switched capacitor works. Let's proceed. Again, this is the T switching time as compared to the signal frequency. Okay, then because of this mechanism, the output voltage now is equal to negative C1 over CF times the input voltage. So we now achieved, or if not totally achieved, but we are now closer to the ideal gain value, which is V out is equal to negative C1 or CF times V in. Okay? Thus, during phase V sub 2, the output signal is an amplified version of the input signal with gain equal to negative C1 over C sub F. The output signal is, however, valid only during phase V sub 2. The fact that the output is valid only during phase V sub 2 is not a major limitation, and the gain can be accurately controlled with the capacitor ratio. Okay? So, in other words, during V sub 1, whatever the output voltage is not counted. It's not valid. Okay? The only output voltage that will be recorded will be the output voltage during V sub 2 period. Okay? The switch capacitor amplifier circuit of figure 2 works well in discrete form, where the parasitic capacitors can be relatively small but in integrated form. The parasitic capacitance from the top plate of C1 also transfers charge to the output, thus limiting the accuracy. Two variants of the switch capacitor amplifier that are insensitive to the parasitic capacitances are shown in figure 5. Okay? What do we mean by parasitic capacitance? Okay? Let's take a look at the meaning of parasitic capacitance. So, parasitic capacitance will exist when two nearby conductive elements are at or possesses different charge levels. Okay, so although parasitic are undesirable, in many cases their effects are negligible and do not pose any major threat to circuit operation. Okay, so these are phenomena which are caused by two plates having different charges. Okay, so where did these different charges came from? Okay, if we go back to so this plate and this plate has different charges when phi sub 2 opens, so they will have, or they will form some kind of parasitic capacitance in between them. Okay, but then again, as we've read from the definition, most of the time the effect of this parasitic capacitance is negligible. Okay, two variants of the switching capacitor amplifier that are insensitive to the parasitic capacitances are shown in figure 5. These are termed stray insensitive amplifier. Okay, let's take a peek. So this is the stray insensitive switch capacitor amplifier. Let's go back. One has an inverting gain and one a non-inverting gain. The signals phi sub 1a are termed advanced clock signals, with the switch phi sub 1a opening slightly in advance of the switch phi sub 1. The advanced clock signal effectively eliminates the signal-dependent delay associated with the slewing of the clock signals. When we say slewing, this is an error on the clock signals, although very minimal. Okay, so this configuration deals with the delay associated by the slewing of the clock signals. Okay. So letter A, we have the non-inverting stray insensitive switch capacitor amplifier. If you look at the switches, okay, this is phi sub 1, phi sub 1, this is phi sub 1a. Alright. Then this is phi sub 2, phi sub 2. Phi sub 1a opens a little bit more advanced than phi sub 1. So this opens a little bit first. A little ahead than phi sub 1. Okay, so this will turn on, and this will turn on, this will turn on. Okay, then charge will flow to the capacitor. Okay, then when the charge flows to the capacitor, okay, so the charges will stay in here because this is closed, and this will open. The charges will stay here, then this will open, this will open, this will open, then this will close. Okay, then the capacitor will discharge to the feedback capacitor. Okay, so this is a matter of timing for the clockings of the switches. Okay, switch first, then next. This is called phi sub 1a and not called like phi sub 3 or something, because the timing of phi sub 1a and phi sub 1 is very near to each other as compared to phi sub 2 and phi sub 1, wherein, as we've seen from the illustration earlier, the non-overlapping time between the two is if not very large, but is very definite or very noticeable or very definite. Okay, so that's it. That's the difference between 1 sub a, 1 and 2. So this is for the non-inverting signal. Okay, so for the non-inverting signal, non-inverting signal. Again, this will close, discharge, charge, open, close. Sorry. This will close and this will close, then it will discharge to until here. Okay, then the second illustration is for the inverting type. Okay, for the inverting type, this will close, charge, right? Then close, then over here, then close, discharge. Okay, so one flow, discharge, one flow, discharge. Okay, so this is for the inverting, this is for the non-inverting. Okay, remember the difference between inverting and non-inverting in our resistor configured op-amps. Okay, so there is a difference in the gain and also in the configuration. Okay, so same with the switch capacitor, non-inverting and inverting amplifiers. Alright, next. Switch capacitor circuits can also be used to build filters. It can be shown that a rapidly switched capacitor acts like a resistor. The basic building block in most switch capacitor filters is the switch capacitor integrator. A switch capacitor integrator is shown in figure 6 along with the continuous time integrator. Okay, so this is the switched capacitor integrator. This is the RC integrator. Okay, so I think this is the one that you're more familiar with. This is the one you encountered for this one. Okay, so if you want to remember a little bit about this RC integrator, okay, so for the RC integrator, we will not derive this one, it will take us a long time again, but I'll just help you remember. Then the capacitor is the feedback instead of another resistor as in the inverting configuration. So this will be, let's just call this R and C. R and C. Okay. So the gain for this one, the voltage gain, is equals to, of course, V out over V in is equal to, okay, so this is 1 over RC, or equal to the time constant, right? Hopefully you still remember your time constant, times the integral of dt. Okay, from 0 to t, or 0 to time. Okay, so this is for the gain of our integrator. So the gain changes over time. Okay, let's go back to the presentation. This is for the integrator. Then, what we're trying to say here is, if a capacitor has a rapid switching like this one, open, close, close, open, open, close, open, charge, open, discharge, close, close, charge, open, close, discharge, open, close, charge, open, close, discharge. If we do this on a very rapid rate, this will be similar to the function of a resistor. That's why, as you can see here, mark is our capacitor and a switch is equivalent to this resistor. Okay, the switched capacitor block in figure 6a, when rapidly switched, performs nearly the same as a resistor in the sense that in any clock period, both transfer charge to the output capacitor that is proportional to V in. The equivalence is depicted in figure 7. The approximate equivalence is given by the expression, the equivalent resistance is equals to, okay, so time, clock over C1 is equals to 1 over C1, the frequency of the clock. Okay, if you're wondering where did this came from, time is in seconds, right? So if you will reciprocate time, that will be 1 per second, and 1 per second is hertz, and hertz is the frequency. Okay, so that's why the reciprocal of time is frequency. The subscript CLK has been added to the period of the clock signal T to emphasize that it is the clock signal. Thus, the unity gain frequency to the integrators are given by, okay, so this is a time constant of the RC, or the resistor capacitor integrator, and this is the time constant for a switched capacitor integrator. Okay, so if you give them same parameters, anyway, what we're trying to say here is that they work in the same manner. Okay, so the other one, only that the other one is the RC integrator, and then the other one is the switch capacitor integrator, and this is the formula for their time constant. Okay, the one that we multiply to the integral of time. Okay, next, the switch capacitor integrator offers two major advantages over the continuous time integrator. So first, large resistors correspond to small capacitors. It can be readily shown that this property makes integrated audio frequency switch capacitors filters viable. The second is accuracy. Since the capacitor ratio can be accurately controlled, and since the clock frequency can be generated by an external crystal, the accuracy of integrated switch capacitor filters can be very good. Okay, sorry, I forgot to mention the clocking that we're talking about since earlier. All of these phi time periods is timed by a crystal oscillator. If you're not familiar with the crystal oscillator, so far that is the most accurate time source. Okay, so it vibrates on a certain frequency. Okay, most of our digital clocks or digital timings are crystal oscillators. Okay. Why? Because when you apply voltage to a crystal oscillator, it will vibrate. So the frequency of the vibration will depend on the power applied to the crystal frequency. Okay. So if you can maintain a constant voltage being applied to the crystal oscillator, you can generate a very consistent timing, very consistent clock. That's why digital clocks are more accurate than analog clocks, because digital clocks are using crystal oscillators. Okay. Next, in integrated form, the switched capacitor integrator of figure 6 is plagued with parasitic capacitances in the same way the switched capacitor amplifier of figure 2 was plagued. Stray, insensitive, inverting, and non-inverting integrators are shown in figure 8. So these are widely used in integrated form. Okay. Stray, insensitive, integrated, and then non-inverting and inverting. So this time we only have phi sub 1 and then phi sub 2. So close, charge, close, discharge, close, straight charge, close, discharge, non-inverting, inverting, integrated form, or integrated form. Okay. Or rather, integrator amplifiers. Next, that's the end of our module.